Welcome to this explainer. Picture this. It's the late 1960s. We're in the absolute thick of the Cold War, and the US is chasing down literally the most ambitious goal in human history, landing a man on the moon. But here's the thing. Amidst all those sleek, incredibly powerful rockets everyone was building, there was this one vehicle that was absolutely essential to the mission, but it was deeply, deeply bizarre.
Right? I mean, you look at it and you think, what happens when you build a spacecraft that can't fly on Earth or even survive re-entry? Because NASA's most critical Apollo vehicle, the Lunar Module, honestly looked like an improvised fragile mistake, like somebody just forgot how to design a spaceship. But there's a brilliant reason for that. It wasn't built for Earth. It was designed to operate strictly out there in the harsh, completely unforgiving vacuum of space.
Now, what's really interesting about this slide is the sheer visual contrast. Just look at the difference here. On one side, you've got the command module. It's sleek, it's heavy, it's packed with dense shielding to survive the searing heat of crashing back into Earth's atmosphere. And then, on the other side, you've got the lunar module. It's got these incredibly thin walls, absolutely zero heat shielding, and it just looks totally weird. Why? Because without any atmosphere to fly through, engineers literally just threw the aerodynamic rulebook out the window.
You see, to actually pull off a moon landing with 1960s technology, NASA had to be absolutely ruthless when it came to weight. So the lunar module had exactly one job. One, land on the moon and lift off again. That's it. It never flies in Earth's atmosphere, and it never comes back to Earth. It's a total masterpiece of specialized engineering, but man, its fragile appearance definitely had people seriously doubting if it could actually work.
And to make this crazy idea work, engineers had to conquer some massive new challenges. Let's talk about the descent engine. This wasn't your typical fire-and-forget rocket where you just light it and hold on. No. Imagine trying to precisely throttle your thrust, adjusting it up and down just to gently touch down this incredibly delicate machine in a total vacuum. That is exactly what this engine had to do.
Okay, so you've landed. But then there's the ascent engine. Once you're actually on the moon, the astronauts kind of need a way to get back, right? This vital engine is what lifts the upper stage right off the lunar surface and back into orbit. And here is the absolutely terrifying reality of this whole setup. Neither of these engines had a backup. No plan B, zero. If you are sitting on the surface of the moon, they have to work perfectly the very first time.
Okay, let's dive into this test. Because before any astronaut was ever going to trust this weird machine with their life, it had to be proven. Enter Apollo 5, January 22, 1968. This uncrewed mission launches from Kennedy Space Center on a Saturn 1B rocket, and its entire purpose? To go into Earth orbit and simulate the exact maneuvers of a real moon landing.
Without this critical test flight, the lunar module was really just a delicate-looking theory. Apollo 5 had to push the hardware to the absolute limit. We're talking about testing structures that had zero aerodynamic stability. If NASA couldn't verify that this fragile craft could actually function in the vacuum of space, well, the entire Apollo program would just grind to a halt.
But what happens when the plan actually fails? Spaceflight is incredibly unforgiving. The plan for Apollo 5 included this very strict, precise series of engine firings to simulate the lunar landing and ascent. But right in the middle of this crucial engine firing sequence, things suddenly went wrong.
Error. Just like that. Right in the middle of the sequence, the onboard computer detects an issue and abruptly aborts. Imagine the sheer panic in mission control for a second. In an instant, this computer abort threatened to completely derail the entire test and potentially delay the timeline for the whole moon landing.
But here's where it gets awesome. Because this apparent failure, it actually turned into a thrilling victory for engineering flexibility. First, the lunar module system safely handled the unexpected abort without completely falling apart. Then, the engineers on the ground rapidly adapted the mission plan right on the fly. They figured out a way to successfully fire the engines in a modified sequence, proving that this fragile spacecraft was actually remarkably resilient.
And you can see that flexibility perfectly illustrated here. Check out the original, super rigid plan, and then look at the results of the modified plan. Despite having to totally abandon their script, they successfully fired both the descent and ascent engines. Even while improvising, they captured the exact vital data they needed to keep the mission alive.
So the crucial point is, the post-flight data from all of this was an absolute gold mine. Engine performance? Verified. The structural integrity of this bizarre craft? Confirmed. The onboard systems? Totally reliable.
Apollo 5 definitively proved that the overall design of the lunar module was fundamentally sound, and that gave NASA the absolute confidence to finally put human beings inside it.
You know, Apollo 5 often gets lost in the history books, right? It's sandwiched between the massive, thunderous rocket tests of Apollo 4 and Apollo 6. But while those missions were out there testing pure brute force, Apollo 5 was testing delicate finesse. It proved out the highly specialized spacecraft that would be the only piece of hardware to actually touch the lunar surface.
And honestly, the pace of progress from here is just staggering. 1968, Apollo 5 proves the hardware works. By March 1969, Apollo 9 puts a real crew inside. May 69, Apollo 10 does a full dress rehearsal at the moon. And then, July 1969, Apollo 11 actually lands. Neil Armstrong's historic footsteps were literally built on the incremental foundation laid by Apollo 5.
Because this is the absolute reality of spaceflight. You don't just build a rocket and launch straight to the moon. Success comes from a rigorous series of tests, adaptations, and constant improvements. The principles they demonstrated during Apollo 5, proving a system under real, messy conditions before you ever risk human lives, that remains the bedrock of modern aerospace engineering, even today.
Which leaves us with a really fascinating question to close out this explainer. We all picture Apollo 11, right? The dramatic astronauts, the flags, the footprints. But are those iconic moments actually built entirely upon the quiet successes that happen way out of the spotlight? Because without Apollo 5, a mission with absolutely no astronauts, a terrifying computer error, and a truly bizarre-looking machine, the iconic Apollo 11 moonwalk would literally never have been possible.